Hello, everyone. My name is Skylar Rodriguez, a current biochem student at UT Austin. This week, we'll be focusing on the fundamentals of chemistry. But before we can even get to the tip of the iceberg, we have to understand measurements, metric prefixes, scientific notation, and conversions. Let's start with the SI unit system. The SI unit system is built upon seven fundamental base units that measure independent physical quantities. The majority of the world uses the metric system and follows the SI unit system, with a handful of countries such as the United States that use the imperial system, aka feet, pounds, inches, and Fahrenheit. So do not stress if this is all relatively new to you. The SI unit system uses kilograms, meters, seconds, Kelvin, amperes, moles, and candelas. For chemistry specifically, we will be working with grams, Kelvin, and moles. We're going to start off with grams, which is represented by the symbol G. Grams are a unit of measurement for the mass of an object. If you take a plastic box, as I've drawn here, it's a mass. Its mass is determined by how many atoms of plastic are packed inside it. No matter the location or gravitational pull, the mass of the object remains constant. Now, it's important to not confuse mass with weight. Weight is calculated using mass times gravity. So, depending on whether you are on Earth or on the moon, it will fluctuate, say from 686 newtons to 114 newtons. But you will remain the same 70 kilograms. Then the unit, the next unit is Kelvin, which is the primary measurement of temperature in science. Instead of measuring how hot or cold something feels to us, like Celsius or Fahrenheit, Kelvin measures how fast atoms are moving. The theoretical point where all atomic movement completely stops is called absolute zero. You cannot get colder than 0 Kelvin, as atoms are at a complete standstill, which means the Kelvin scale has no negative numbers. If you wanted to know how cold that is in Fahrenheit, it is negative 459.67 degrees Fahrenheit. Now, it's important to important reference points are that water freezes at 273.15 Kelvin or 0 degrees Celsius, and water boils at 373.15 Kelvin or 100 degrees Celsius. Now we're going to go to the mole. As you can probably assume, I'm not talking about the cute little animals that dig in the dirt. In chemistry, a mole is simply a counting number similar to the word dozen. If I say a dozen eggs, you instantly think of 12 eggs. A mole refers to 6.02 times 10 to the 23rd power of atoms. This is also called Avogadro's number. This is a massive number because atoms are extremely tiny. You cannot simply weigh a single atom, but rather, if you gather a mole of it, let's say carbon, it weighs exactly 12 grams. So while grams measure how heavy something is, moles tells us how many particles slash atoms are inside that mass. Now, you probably noticed that Avogadro's number, the 6.022 times 10 to the 23rd power, looked a little different. That is because it is written in scientific notation, which is an essential tool to describe extremely large and small quantities, like septillions of atoms or tiny mass of an electron. Writing down number of zeros takes forever and leads to mistakes. Scientific notation solves this by condensing numbers into a simple format: n times 10 to the power of x. N is the number between 1 and 10. X is the exponent, a power of 10. If there is a positive exponent, it means it's a larger number, more than 1. You move the decimal to the right. For example, 3 times 10 to the third power is equal to 3,000. When it's a negative exponent, it's smaller, less than 1. You move the decimal to the left. For example, 2 times 10 to the negative 4 is 0.0002. I think I didn't add an extra zero. Um, now, now that we've gone over the most common SI units and scientific notation, we will discuss the different metric prefixes. Metric prefixes are just shortcuts for powers of 10. Instead of writing 0.001 grams, we say 1 milligram. The golden rule for conversions is to recognize that going from a large unit to a smaller one makes the number get bigger by moving the decimal to the right. Vice versa, if you go from a smaller unit to a larger unit, you will move the decimal to the left. An example of this would be converting 3 kilograms to grams, which comes out to 3,000, grams. I'm going to write out a table that will allow you to see the key prefixes in chemistry. So here we have prefixes, symbols, meanings, and the scientific notation. There is mega, which is symbolized by the capital M, which is to a million. And the scientific notation is 10 to the sixth power. Kilo, which is with the symbol of K, is to 1,000. And that is to 10 to the third power. Base unit, grams, meters, liters, this is 10 to the 0. It's just 1, you know? Centi, which is C, is 1 divided by 100. And this could be represented as 10 to the negative 2 power. Milli, M, 1 over 1,000, 10 to the third power, negative 3 power. Micro, which is the symbol of I believe. 1 over a million, which would be 10 to the negative 6 power. And then nano, represented by n, a lowercase n, 1 over a billion, which would be 10 to the negative 9 power. Now, knowing the metric prefixes, let me show you how to do conversions. The trick is to keep track of the power of 10. Ask yourself, am I converting to a bigger or smaller unit? If you're converting from a large unit to a smaller unit, you multiply. If you're going from a smaller to a larger unit, you will divide. Let's go back to my original example. How did I figure out that 3 kilograms is 3,000 grams? You first thought should be to recognize the word kilogram. The prefix kilo means 10 to the third power, which is also equal to 1,000. So now I will multiply 3 times 1,000, which gives us 3,000 grams. Now, let me show you an example of going the opposite way. We'll start with 200 milligrams and convert it to kilograms. I'm going to show you the long way to do this, then the short version. We're going to first convert milligrams to grams. We know that a milligram is 10 to the negative 3 power of a gram, or 0.001 of a gram. If you don't know how we got the value, when you see 10 to the negative 3, move the decimal place of the number 3 of the number 3 times to the left. So 200 milligrams divided by 1,000 is equal to zero point 0.2 grams. Now we need to convert grams to kilograms, which is 10 to the third power, meaning we essentially move the decimal place 3 times over to the left. But first, to show our work, 0.02 divided by 1,000 equals to 0.0002 kilograms, or 2 times 10 to the negative 4 kilograms. The short route would be to look at the total change in powers of 10. Moving from 10 to the negative 3 powers, which is milli, to 10 to the third, which is kilo, is a difference of 6 powers of 10, 10 to the 6. Since you're going from a smaller unit to a larger unit, shift the decimal point 6 places to the left, making it 0.00200 kilograms, or 2.0 times 10 to the negative 4 kilograms. Now that I've shown you how to convert, I'm going to write down 3 different examples I want you to do to see if you can do it on your own. And I'll give you just a couple seconds so you could just pause it. The first question is going to be 12 millimeters to liters. Next one would be 36 kilometers to meters. Then convert 6 micrograms to grams. All right, that should be enough time. Now we're going to go over the solutions. So simply, I divided 12 over 1,000, which equals to 0.012 liters, or 1.2 times 10 to the negative 2 liters. 36 times 10 equals 36,000 meters, or 3.6 times 10 to the fourth power meters. And then for the last one, we're going to do 6 divided by a million, which equals to 0.000006 grams, or 6.0 times 10 to the negative 6 grams. I hope you all enjoyed this video. This is my first one, so sorry for it being a little choppy. Hopefully throughout the semester, it will get better. I will leave a link to a practice exam you can take on the topics we discussed today. The next video will focus on sig figs, accuracy versus precision, and classification of matter. See you all then.